Rich and Vin tackle two separate topics on this week's podcast. First, what does it really mean to be AI-enabled? Second, we dissect ARM's recent announcement that it will become a silicon provider in addition to being an IP provider. Good afternoon. Welcome to another edition of DevTalk with Rich and Vin. I'm Rich Nass with Embedded Computing Design. The guy in the funky looking tie there with the, I don't know, does that match? Would my wife allow you to wear that outfit?
I don't know. I don't know if she would or not. I have subscribed for a long time with two fancies in a plane. So you can't have three fancies, but you could do two fancies in a plane. So tie and shirt and plain jacket, or plain pants, or tie and jacket and plain shirt. So two fancies in a plane has been my sort of signature look. And this actually came to me from a private shopper at Nordstrom's years ago. I had a private shopper at Nordstrom's. So there you go.
I disagree, but that's neither here nor there because I have never been accused of being a fashionite. No. That is certainly for sure. Okay, so Vin D'Agostino, the other guy on the other end. How are you doing, Vin?
Two fancies in a plane. I'm doing great.
Very good. But does the plane mean airplane?
Sometimes I've been traveling a lot. For those who are listening, where I'm actually doing this remotely at a client's office because we've been trying to do this and I've been traveling so much.
Okay. One of these podcasts that I want to do later on is, I actually wrote this down and it's a really good topic. Is there life after 60 for an engineer who's looking for a job? But don't comment on that because nope. I know you can talk about that for quite some time, but we want to talk about something else today. But that's a good one.
That is a good one. Let's put that on the list. Absolutely.
Okay. So what I want to talk to you about today, I actually had this discussion with a guy from Infineon and on the Embedded Executive podcast, which just came out this week or last week. But I'd certainly like to hear your take on this as well. What is the real definition of artificial intelligence, and are we applying it properly to the products that are out in the market? And where I'm going with this, I guess, is it marketing spin, or is it really artificial intelligence? And I know I have my opinion, but I'll let you talk first.
Well, I mean, let's talk about the marketing spin first, because that's the easy part to talk about before we talk about the technology. If you think about it, and you talk about life after 60, you and I are old enough to have lived through a bunch of these technological marvels. When I graduated from Stevens, it was when I started as a freshman, it was the first year they weren't teaching tubes, right? So things went from tubes to transistors, and everybody was selling things that were called solid state. And then after that, when MCUs and stuff became available to everyone who wanted to design with it pretty easily, everything was suddenly smart, and people were putting smart on the boxes of their products. And then when IoT came around, everything was connected, and now everything is AI. So for every one of these technologies, there is a marketing spin because people are looking for market share. And for those applications where you're just putting a label on a box, the definition is pretty thin and pretty flexible, right?
We'll stop there. Okay, what is a thin and flexible definition? What can you do? Name a product, whether it's a white good, whether it's a router, something else. What's passable?
I mean, let's talk about refrigerators, right? You could say that a refrigerator is AI if it's doing something like counting the number of times you open and close the door and how long it's open, and using that to predict where the temperature is going to go, and add more refrigeration when the door is closed before it senses that the temperature has dropped. Because if you think about the physical mass of a refrigerator, it's radiating heat or accepting cold, right? Even when the door is open, but just less. And so you won't necessarily see that right away. But if you know something other than what you're directly measuring, which is the temperature, you may be able to do something to affect it and therefore keep the temperature stability closer to normal. And you could call that artificial intelligence because you are using other information to not measuring temperature to control temperature. So
I
how much
think
of
in
that you
this
do?
in this first round of products, it's far simpler than that. It's just
Uh,
find me something that I can call AI so I can put it on the box.
Yeah,
Like,
100%, 100%.
is there enough ice in the bin right now, or do I need to make more ice? And I think what you're referring to is real and actually will make a difference, but I don't see that sort of stuff happening yet.
Right, but I mean, it is real, and you could say it's artificial intelligence, and we'll talk about that in a minute. But there's so much more that you could do. You could be analyzing the air in the refrigerator and determining spoilage of foods. You can potentially monitor the air and figure out what foods are in what cavity and keep it at different temperatures. I saw an
But
interesting, I listened.
at what cost? Do you want to spend an extra $2,000 for a refrigerator that's going to save you 50 cents in energy a month?
Is it 50 cents in energy? Is it $2 or $3 in food? Or is it the fact that you thought you were going to be ready to make dinner tonight and you pulled something out and it spoiled and you didn't realize it, and now you're scrambling to make dinner? So some of it is cost, some of it's
Or that you could
convenience,
tell all your friends that you have an AI
or you
refrigerator?
can tell your friends that you have an AI refrigerator. Yes. Um, I was listening to an interesting podcast on refrigeration, and people will be like, "You're listening to podcasts about refrigeration? You have no life." But it was very interesting, the
He's
history
really
of
cool.
yeah, it was very cool actually. But it's actually something that's pretty rich history. And they talked about a whole bunch of foods and the slight difference in temperature that determines how fresh, how long they stay fresh, right? Different vegetables, different fruits, different meats. And so, if you have the ability to detect that, now you are actually making some intelligent decisions about how you keep your food stored. And I think that is really what it's about, because it's not, for me, artificial intelligence, especially on a device, is really simple. You are using statistics and aggregated data and some analysis to be able to predict the value of something that you can't measure directly. If you can measure temperature directly, you measure it and you take action, turn on, turn off, whatever you're going to do. But let's say you have 6 sensors around a space and you need to triangulate the temperature in different parts of the space. Well, if you assume it's static, it's simple math, right? Very algorithmic. You take these things, you know the distances, you do some mathematics based on thermodynamics, and you're all set. But what if you're monitoring people walking around the room? What if you're monitoring doors getting opened and closed?
Oh, that's the
Now,
key. Dynamic. You're monitoring dynamic things. Okay, I didn't
yes.
I didn't see where you're going. Now I understand.
Yeah, so see, that's the thing. You are. It's funny. I went to a very well-known university years and years ago when I was at Renesas, and we were just starting to look at AI and stuff. And they are very famous for AI, and they rolled out the red carpet for me. It was a lovely day at the school, and at one point they had me meet this professor. She was working with municipalities on using AI to predict pothole size and when you should deploy trucks to fix the pothole. And I'm thinking I'm going to go in there and they've got cameras at every corner and they're monitoring cars and trucks in and out, and they assume the weight and they know the temperature and they know something about the soil underneath. And just from that information, they're determining whether a pothole exists on the street. That's not what they were doing. They were finding potholes and pointing cameras at them and supposedly using AI to determine when the circumference of the pothole was big enough to send a crew out. Well, I don't know why that's AI. I mean, that's just kind of crazy, right? Um, I mean, that's a simple circle. A lot of potholes are round or they're rectangular because it's either a trough cut by by a tire, or it's a sinkhole in the middle. And so those equations have been known since Archimedes. So I'm not sure why that's artificial intelligence. So, and that was, a decade ago. So I'm sure they've gone well past that. And I
So what
think
is artificial intelligence today from a technology perspective? Looking at the MCUs that are out there that people are putting in these devices, what makes them AI MCUs?
okay, AI MCUs is different than AI as a technology. An AI
Yes.
MCU would
Well,
have an
I mean, we
accelerator,
have
for
to stick.
example.
I'm trying to stick to our audience.
Yeah, so if you have some hardware acceleration modular in the silicon that is helping you get AI done faster, you could call that an AI MCU. there are companies, and you and I have talked about this. Renesas owns Reality AI. They are an AI company doing embedded AI, and they are basically using the DSP extensions of the ARM instruction set and using DSP to analyze streaming data from sensors and applying AI techniques to that data to
Okay,
make
stop.
some determinations.
Applying AI techniques. What does that mean?
Uh,
What are
you
AI
are
techniques?
Okay, so you are training a model on what it means to, okay, here's a good example. Those of us who are old enough to have done Carnot maps to reduce digital equations and digital circuits realize that you have things that are called don't cares, right? Where it doesn't matter whether it's a 0 or 1, it doesn't affect the output. And you do that to initially to minimize the, okay. So if you think about all the data you can take on a system, let's say you have an HVAC system and you've got maybe 120 things that you could measure, and you're looking for certain things. You're looking for low refrigerant. You're looking for, is the indoor air coil blocked? Is the outdoor air coil blocked? Is the fan blade outside no longer balanced because it got hit by a piece of hail and now it's spinning off center, right? These are all conditions that can happen. If you want to measure those directly, you're looking at flow sensors, you're looking at accelerometers, you're looking at pressure sensors. You are probably adding a couple $100 to the bill of materials plus all the wiring to get them all set up. That's a non-starter for certainly residential, if not some small commercial systems, right? That's a high percentage. But what if there's other data you could look at, the different phases of current going out to the motor to see if there is a change in imbalance? What if you could look at incoming and outgoing refrigerant temperatures to see if you're transferring the amount of heat that you expect to, and that'll tell you whether there's airflow, right? These are all things where you are measuring, you're predicting airflow, let's say, based on how much heat comes out of or cool comes out of a refrigerant through a coil that is well known. You need to train it. You need to say, this is what normally happens at this outside temperature, this inside temperature, blah, blah, blah. And you build this matrix and these patterns, and then you compare it. So you have maybe 120 things that you can measure in the system. You measure all of it and you look at it and say, well, these 4 conditions are the things that change when my trigger point, if you want to call it that, my condition that I'm trying to test for occurs. So now you've built up all this data. You've done your don't cares. I don't need to look at these 117 pieces of data. I only need to look at these 3. So the experimental part at the beginning is key to efficient AI. And now you're only looking at the things that really matter in concert with each other. And you're using those things to predict something that you're not measuring directly. You can now do that $200 worth of sensors, if you could work it out, for probably a bill of materials of under $5, right? That's a couple of thermocouples and maybe something measuring, I don't know, the vibration of something, the position of something.
I think you just spun it back to the refrigerator at that point.
Certainly this could happen in a refrigerator too. I mean,
yeah. I mean, to do predictive maintenance for something like that, to know when the fan is a little bit off kilter and that kind of thing, or okay.
Yeah, I mean, I'll share with you a really simple example that somebody gave me early on to talk about AI. He said, let's say you're in a car and what you have access to is speed and acceleration, right? And you make an XY axis. If you have a lot of acceleration and deceleration and low speed, you could probably predict that the car is in the city. If you have a lot of speed and not a lot of acceleration or deceleration, you could predict that it's on the highway. If you also, for example, knew the position of the steering wheel, you could determine whether it's in the city or in a parking lot, right? So these pieces of data, and now you're not measuring with a GPS where you are, but you are using other data to say, hey, this seems to me like they're moving on a highway, or this seems to me like they're moving in a city. I think that's a pretty illustrative example of how you can use secondary data to predict the thing that you want to predict. So, and that is something that what you want to do and how you want to do it will also help predict whether you're going to do it on the device, on the edge, in your space on the gateway or on a little server on your LAN where the response time would be a little less than on the device, but faster than in the cloud, or whether you're going to go out to the cloud. And it's how much horsepower do you need? How much data do you need to push? Imagine trying to look for frequencies of vibration with data in the cloud. You either have to take a sample and push the whole sample up, or you have wide bandwidth where you're sending all the samples up. That is costly on storage. It's costly on server. It's costly on bandwidth, right? But if you could do it locally on the device, you're saving all that. And then on top of that, think about the privacy of your data, right? That if you're doing it locally on your device, it never even leaves the device, let alone your LAN. Putting stuff in the cloud, you never really know where it's going to go. So these are all considerations in whether you're going to do it on the edge, on the device, or in the cloud. And all of that determines whether you're really doing AI or whether you're just relabeling something that you were doing kind of like AI, so you could put AI on the box. But
okay, let's shift gears completely because I think we've talked about that one. Because we're not out of time, but I don't think we have a deadline on time. But
I know it can only take so much of me. So
you've mentioned Renesas a few times, and some of their competitors are having to deal with some news that came out not too long ago from ARM. ARM has been the supplier for the Renesases, the STs, the NXPs for decades. All of a sudden, ARM will be a silicon provider and will be a competitor to these other big silicon providers. What does that mean to somebody like a Renesas?
I'm not too worried about it.
Well, you don't have to worry, but
I don't have to worry
Renaissance?
about it. I mean, I think certainly if they can make some general purpose devices cheaply and they have a deep understanding of the core, they might be able to give some good support. But when I talk about MCUs all the time, I talk about electronics, I always say, look, MCUs, MPUs, to some extent, and programmable logic are the only devices in our industry where the intellectual property goes into the device instead of around it. What do I mean by that? If you have an op amp in a circuit and you look just at the two inputs and the output, those look exactly the same, whether it's a filter, whether it's an amplifier, whether it's a level shifter, because the device always does exactly the same thing at its pins. And you put your intellectual property on the circuit board around the device to realize the solution that you're looking for. With things that are programmable and the programming goes inside, you are putting that solution inside the device, and the pins functions can change dramatically based on the firmware that you put in. And so you're not just picking a core or picking a clock speed or picking an amount of memory. You are picking, if you pick the right part, you're picking a complement of peripherals that will help you do your job small, inexpensive, and fast, right? So the key to good MCU design, especially, is the design of the peripherals, not the design of the core. Look at ST, look at Microchip, look at Renesas. They all built businesses without ARM, well before ARM came out, right? And even Renesas has RX and RL, two very good performing on power or on compute. I would say that the V3 RX core, transistor for transistor, outperforms the same device in ARM. It doesn't have the ecosystem globally that ARM has around it because of the ubiquitousness of ARM. Okay, fine. It's about the peripherals. How good is your A to D? How flexible are your timers? How long are your timers for doing, long-term delay? What does your interrupt chain look like? How good are your D to A's? Do you have comparators on the chip? People poo-poo the analog side, but MCUs are mixed mode devices, 100%. I remember when I was at Renesas and we were looking at a silicon on insulator process, everybody else in the industry who was playing with this was trying to maximize clock speed. They wanted to make the fastest device possible for the lowest power. Renesas said, you know what? I'm not worried about that because I've got analog on here. I want the lowest noise analog. So when I wake up and I take a piece of data and I go back to sleep, I know that data is good. I have worked with so many 12 and 14-bit A to Ds on somebody's part, and maybe you're getting 10 bits out of it, right? You look at a good A to D peripheral, and if it's 12 bits and you can get 12 bits out of it, if your process is good, if you understand analog design. And I'm not saying that ARM can't hire analog engineers, but hell, these people who have been supplying these mini cities on a chip have been building these building blocks for decades, and they know where all the bones are buried, and they know how to get really good performance on peripherals. Are they going to be a strong player? Of course, they're going to be a strong player because of who they are. But for my money, I would use a Renesas peripheral every time. They have really worked hard on making sure that their peripherals are top notch, both in power consumption and performance, and even physical size on the die, which means lower cost. So I think they'll be a strong player. I don't think good silicon companies who have really good peripherals and a strong ecosystem already have to worry that much. The ecosystem is going to be the big thing. There is such an ecosystem around ARM in general now that if they start building the ecosystem around the devices, that's going to be the thing that's going to push people, especially the mass market, because they are looking for solutions at midnight. So they're looking for community support. They're looking for really good documentation. They are, and so that's going to be the play.
Yep. The other thing I see there, loyalty for an engineer is huge. Getting an engineer to switch from one vendor to another, you have to, it just doesn't happen. We've been doing these studies for years and years and years. Which architecture do you use, and what would it take to get you to switch? And they just don't want to switch.
Yeah, I mean, some of it is loyalty to the company, some of it is loyalty to the local supplier, although there's less of that now. When you and I were young engineers, you'd have small distributors everywhere. They would come in, they'd spend time with you, and now it's like
it's fear. It's fear.
Well,
this works.
It's fear.
This thing works, and I know it works. That one might be 4% better, but I'm not taking a chance that that's the way that I see it.
Yeah. I mean, I do a lot of marketing consulting around technology, and I always hesitate when someone says, well, my competition is doing this, we have to close the gap with the competition, or we have to be more like them. You should know what your competition is doing. I'm not saying ignore your competition. That would be a silly thing to say. But you are not measured against your competitor. You are measured against your customer's needs. So if you understand what your customer needs and you close that gap, by definition, you'll be closing the gap with your competitors. Because if you get to be as good as your competitors and you spend that money, there's still no incentive to switch. You need to be better. And what does better mean? It means that you're solving your customers' problems better. So being more intimate with your customers' needs and moving in that direction will automatically differentiate you from the competitors and help switch. The statistics on people switching is amazingly, it's like 6 or 7% or some ridiculous number. I mean, it's just crazy. You've got to really demonstrate a difference.
And it's only because a bean counter found something cheaper.
Well, that's how ARM, ARM did a bunch of smart things. One of them was their university program, where they really got kids in school to get familiar with that architecture. And there were so many different architectures that when they came out of school and needed to pick a part, they picked the one that they knew from school, right? So that was a really, and I got that word right from somebody at ARM that I happened to meet on a plane, and we were talking about it. But the other thing, besides the ecosystem around it, is getting the purchasing people to believe that you can replace any ARM part with any ARM part. And they thought they could pit Renesas against Infineon against ST because it wouldn't matter what the socket looked like, right? And of course, engineers know that that's not possible. It's possible, but not probable. And you saw that during the pandemic, where people couldn't get parts and they tried to move to somebody else's ARM part, and it was tons and tons and tons of code work, right? To make that happen. So I think that was the promise that made engineering managers say we're going ARM, and helped to kill a lot of the proprietary architectures. So those were the three things: the ecosystem, the promise, the false promise of being vendor independent, right? Vendor agnostic, and the ecosystem around the part. So
Very good, Vincent. Always good to chat with you.
yeah, it's great to chat with you.
I love your perspective. I don't really care for your tie, but I do love your perspective.
You know, we should take a picture of this and post it on the website and get people to vote. Two
All right.
fancies in a plane. I have a very plain jacket that I have over this, just so you know.
I think that is a non-truth because you have nothing that's plain. All right.
All right, Rich. Great
Let's
to talk
put a
to you.
wrap on this, and we will see each other on the next episode. This has been Dev Talk with Rich and Vin.
Cool. Thanks. Bye-bye. Bye, everybody.